So in this section, we're doing 2 sample confidence intervals. So as we set the scene, suppose we want to compare the proportion of individuals within a certain characteristic in populations A and B. You know, maybe we're trying to compare a proportion for maybe comparing between males and females. Yes, did I not push it out to you all? All right, let me push it. Let me push it. You guys. All right, should start coming out there pretty soon. We'll pause and we'll talk about it. So I'll just keep ad-libbing until you tell me it's okay. So again, let's say we want to compare something between males and females. Is there a difference maybe between teens and adults? Basically, we got 2 populations. We want to find, is there a difference in the 2 things? Now, the sample sizes do not have to be the same size. So we can have different sizes for each of the populations. Did it come out there yet? Are we good? Okay. So now the idea strategy, as we look at it, the ideal strategy is to take a separate random sample from each population and compare the sample proportions P1 hat and P2 hat with that characteristic, whatever we're trying to look at. We compare the populations by doing inferences about the difference meaning the subtraction between our P1 minus P2. Is there a difference between the parameters? The statistic that estimates this difference is the difference between the sample proportions. So that would be P1 hat minus P2 hat. Okay, so we're trying to see, in our samples, is there a difference, and therefore we can infer to the bigger population, is there a difference between those populations as a whole? When we analyze the sampling distribution of difference of 2 proportions, we know that the individual distributions, this P1 hat and P2 hat look like, but are not, but not exactly, but it should be about what P1 and P1 hat minus 2P2 hat. Sorry, I got the tongue tied on that one. So when we go to decide, can we do this process, we always got to check normality. So in this case, when we check normality, it's a lengthy process. We got to do sample 1 times P1 hat. Is it greater than or equal to 10? Is my sample 1 times 1 minus P1 hat, is it greater than or equal to 10? Then I have to do the same thing for the other sample. So then I have to do sample 2 times P2 hat. Is that greater than or equal to 10? Is sample 2 the size times 1 minus P2 hat? Is it greater than or equal to 10? So I got to now show 4 things to decide, hey, am I approximately normal? Where is our center? Well, we know the center is the mean. Well, in this case, it's going to be the mean of P1 hat minus P2 hat. Now, how do we calculate that? Well, that's just the difference between P1 hat and P2 hat. That's all it is. The mean of it, the center of the difference, is just taking the 2 individual P hats and subtracting them. When we combine 2 distributions, we can't just combine the standard deviations. We learned that before. We have to turn them into variances. So our formula now for the standard deviation of, again, these all should have hats. I copied a picture so I couldn't doctor it. So these all should have hats on here. So in order to find the standard deviation of the difference between our two things, we would turn them into variances by squaring them, add the two things together, and then take the square root. So the way this looks like, since we turn it would be a big junky formula. It would be P1 hat times 1 minus P1 hat over N1 plus P2 hat times 1 minus P2 hat over N2. There is our formula. Now, typically when we're finding standard deviations, and we'll touch on this in a moment as well, but in order to touch on it, we say, what do we have to make sure in order to do the standard deviations? We have to meet what condition? Anybody remember what condition we got to make sure we meet in order to do that? We got to do independence. So what do we do for independence? We know it's not sampling with replacement. So then what's our other option? What grade you were in 2 years ago, except for one of you was 1 year ago? What grade were you in 2 years ago? Yeah, so we multiply by 10. Okay, multiply by 10. So remember, the independence, for independence, when we check the independence, that's that 10% thing. So is 10 times little n, is it less than or equal to capital N? We're checking that clause. If we meet the independence for that purposes where our sample times 10 is less than or equal to the big population, then we can go ahead and do that standard deviation change. We can do that formula. If it's not, then we don't do it. So again, we jump pretty quick into an example here. Now, they will always tell us how they want us to set up the difference, okay? So in this case here, they tell us, I'll just point it out real quickly, they tell us that we're doing P hat M minus P hat J, or PJ hat. So they will always indicate which way to do the difference. Because we know when we subtract, there is a difference between the two answers. So suppose that two counselors at a school with more than 2,000 students, Michelle and Julie, independently take a random sample of 100 students from their school and record the proportion of students that did their homework last night. At the school, supposedly, 70% of the students completed their homework last night. When does night stop? That's the big question. All right. So when they are finished, they find the difference in their proportions. So there's the PM is Michelle and the PJ is Julie. So the difference between the two proportions was 0.08. They were surprised to get a difference this big. There was an 8% difference between the two, considering were sampling from the same population. They first asked us to describe the shape, center, spread, and sampling distribution in this problem. All right, so we got to do the shape. Now, we don't have a picture to go by. We got to do the center. And then we got to do the spread. Okie dokie. So the shape. Well, first thing we got to decide, is it normal? So if I'm trying to decide if it's normal, then that means I got to do that NP stuff. I got to do the NP greater than or equal to 10 for each of the stuff. N times 1 minus P greater than or equal to 10. And again, I'm using P hats, and they all have their own little subscripts. So in this case, we would start off with saying, all right, I did 100 students. Probability to supposedly that they did their homework 70%, so 0.7. Is that greater than or equal to 10? Well, that's 70. That's greater than or equal to 10. So yes. Now I do the other part of it. So 100 times 0.3. And then that would give me 30. That's greater than or equal to 10. Now, they didn't give me another sample. Sometimes they give us a totally different sample. So in this case, they said both of them did a sample of 100. So this time I would have to repeat it. So this technically first one is the N1. And then now I got to do it again for N2. So now I go through and show the exact same thing I did. We cannot just get away with not doing it. We have to. They will not give you credit for this part for checking normality. So we would have to go through and show this real quickly. Again, sometimes it's petty, but when we think about it, there's a lot of times we get to use the calculator to speed up processes, so the least we can do is show the math work and show the setup of stuff. So with that in mind, since all those are okay, we can say that it's approximately normal. Approximately normal, since all of those were greater than 10. So there's our shape. If one of them was not greater than 10, then we would stop and we would say, hey, not. The difference between the two is not normal. And that's as far as we'd probably go. We would just say not normal. We wouldn't say it's skewed. We just say it's not normal or not approximately normal. The center, well, that's the mean. So in this case here, P1 hat minus P2 hat. I want to find the mean of the P1 hat minus P2 hat. So that's just P1 hat minus P2 hat. Now, granted, they gave us M's and J's. So PM hat minus PJ hat, which would be 0.7 minus 0.7, which gives us 0. So we're expecting there to be no difference between the two. Now, spread. Spread, we're using standard deviation. Well, before I got to do that, I got to check what? I got to check independence. So 10% rule. So with that in mind, 10 times 100 is 1,000. 10 times 100 is 1,000. Got to check both. All right. Now, it does say that there is more than 2,000 students in school. So we are less than 10%. Both samples are less than, that and individually. So we're still good. As long as both of those, 1,000 is less than 2,000, hey, we're good for both of these. So we are independent. We don't have to combine them. We have to check each sample size separate. So now that lets me know I can go ahead and do the standard deviation stuff. So as I eat up a lot of my space over here, the standard deviation of PM hat minus PJ hat, big square root, 0.7 times 0.3 over 100 plus 0.7 times 0.3 over 100. Again, they said it was 70% was the P, so then 1 minus 70 is the 3. So that would give me the square root of technically 0.21 over 100 twice. I have it down there. So that is the square root of 0.42 over 100. And then when we look at calculator, I can do the square root of 0.0042 is what I can type in. Now that's a little bit nicer to type in. That comes out to be approximately 0.0648. So the spread is about 6%, 6.5% is the spread. All right. Anybody need my purple chicken scratch off to the side still? Ooh, yeah. Oh, man. Slow delay on the Wi-Fi there. There we go. Now they on the next part they ask us a question on what's the probability. All right, what's the probability? So now we did say our shape was what? How do we characterize our shape? Normal. So if I characterize something as normal and I'm asking for a probability, then what does that mean I could probably use? Normal CDF. Okay. So again, whenever we can do that, that makes life a lot easier. If we can get it to be normal and stuff, then we can use that feature. So They're asking us find the probability of getting two proportions at least 8% apart. All right, well, so what's that probability? So when I look at my picture here, I know the mean is in the middle, 0. They said my standard deviation was 0.0648. So that tells me this line is 0.0648. The second deviation would be 0.1296? 0.1296, I think. All right, and then this way would be the opposite, negative 0.0648. And then that one would be a negative 0.1296. So now they said at least 8 apart. So when we think about those decimals I just did, 8% is right about there. Now, at least means what? Doesn't at least mean greater than? Doesn't at least mean greater than or equal to? So that means at least greater than or equal to that 8% on the graph. Now, here's the thing. Not only is there a version on the right side, but there's technically a version on the left side. There's a shaded instance here. Because as if we think about it, what happens, like right now, the way we have it set up with PM hat minus PJ hat, if the difference is positive, then that's represented by the stuff on the right side of the normal curve. So that means that Michelle's percentage amount for her sample was bigger than was it Julie? Like that one, Julie? So, whereas the left side that I have shaded represents Julie's percentage being higher than Michelle's. Okay, so there's actually 2 shaded zones here. So, and that's a big deal because it comes into play in our normal CDF. So, we know we when we look at our normal CDF, we know we're doing a normal CDF. Normal CDF. Now, I'm going to use my lower bound is 0.08. At least, so my upper bound, we can go 100. We're talking about percentages. Okay, and then my mean is 0. My standard deviation, I'm going to type in that square root number, square root of 0.0042, because I want it to be accurate. So I'm going to go back to using that. I don't want to don't use a rounded decimal in the normal CDF. Now, this represents the area in one of the zones. That technically represents kind of the area over here to the right. That's what that formula represents. I have to remember that there's two zones. There's one on the right and there's one on the left. So I got to multiply that by 2 to get my final probability. So now I'm ready for the calculator. And then I'm going to go in here. Let me get rid of my data. Second plus 712. And then we're going to go second vars, normal CDF. 0.08 is my lower, 100 is my upper, mean is 0. This is where I'm going to put the square root of 0.0042 just to make it as accurate as possible. Go down, hit enter a couple times. Now, just the area to the right is 0.1085220184. I now need to make sure I include the area on the left. So I gotta basically multiply that by 2. And that gives me a final probability. The probability that x is greater than or equal to 0.08. Again, doesn't matter if it's greater than 0.08. The positive, also on the other negative side, is approximately 0.2170. There's a 21.70% chance. There's a 21% chance, almost a 22% chance that probability that the difference between the two will be greater than 8. All right, then follow-up question. Should the counselors have been surprised to get this big of a difference? In this case, we would say no. No. they should not be surprised to get a difference as big as 0.08 because there is a 21.7% chance of this happening. Again, what do we use typically as the benchmark for deciding if it would, like, we should be surprised? What percentage do we roughly use? It was usually around like 5%. Okay, you know, if it was less than 5%, the closer we got, smaller than 5%, we should be really surprised. It was unusual to get something that thing, but again, this big of a percentage, a 20% chance for this to occur, they should not be surprised that they got a difference of 8% or more. Okay, that probably should happen. Okay, so that's where, again, as we look at problems in the applications, we can tie in the probability aspect of it. So we're going to get into a actual physical doing a confidence interval thing here in a moment. So confidence intervals for P1 minus P2. When data comes from two random samples, or groups in a randomized experiment, the random condition, remember, we got to make sure we hit that random condition. Our statistic, the statistic that we're going to be doing is P1 hat minus P2 hat, is our best guess for what P1 minus P2 is, the population parameters, the difference between the two population parameters. So again, when data comes from two random samples or two groups in a randomized experiment, the statistic, when we find the P1 hat minus P2 hat, is our best guess for what the true parameter is, the true value for the difference between the two. We can use our familiar formula to calculate the confidence interval for P1 minus P2. All right, we're allowed to do that. Since we don't know our true standard deviation, we replace P with P hat to get a standard error, which is our estimated standard deviation of the P1 hat minus P2 hat. Again, here's our, remember, if I meet the 10% condition, then I can find the standard error. I can do the standard deviation part of P1 hat times 1 minus P1 hat over N 1 plus P2 hat times 1 minus P2 hat over N2. Again, make sure we check for independence for both samples. So we're going to just walk through a little bit of the setup of one, and then we're going to actually do one here in a second. So when we look at our doing a confidence interval for the difference in proportions between two proportions, first as we look at our statement phase, we're going to estimate the difference in the proportions of, and again, they tell us the order, so the difference between this first one and this second one, and then what kind of confidence are we doing? Our plan is to use a 2-sample Z interval for proportions if conditions are met. All right, again, we want to write this in the plan stage. Later on in the deduce stage, we're going to use the calculator code, is what we're going to do. Now, random condition. The data are produced by a random sample of size N1 from population 1 and random sample of size N2 from population 2. Or both groups of size N1 and N2. in a randomized experiment. How would we check for normal condition? This is where we would make sure we'd show that the N1 times P1 hat is greater than or equal to 10. And 1 times 1 minus P1 hat is greater than or equal to 10. And then we would do it for the second sample. All right, now, independence condition. Both the samples or groups themselves and the observations in each sample or group are independent or meet the 10% condition. And I'm just going to cover that up because you really don't need that part. All right. Now our due stage, if the conditions are met, and like typically I would say, hey, conditions are met, we would want to compute out, again, this is the by hand method. If you're going by hand, we would compute P1 hat and P2 hat, and then we would find what is the difference between the two. So that's what we would do if we're doing it by hand. We'd go through, do our inverse norm to find out what is our Z star, or you can use table A. You can use that as well, okay? And then now we would go through and actually compute the interval. So this is where we would go through, and this is a long formula. It would be technically P1 hat minus P2 hat plus or minus whatever our Z star is times the square root of P1 hat times 1 minus P1 hat over N1 plus P2 hat times 1 minus P2 hat times N2. And we would actually do that. That's how we would go about doing it. Now, remember, we have to know that method, how to at least start it. And I would even have it on a free response of always starting it like that. Even if you're going to use the calculator feature to do it. I would just show the setup on a free response of putting each of the values where they're at. Just don't simplify. Because technically if you get credit for the work, showing the original formula, that filled in with the numbers, and then you can just put equals and then what the answer is. And you can grab the answer from doing a 1-2 prop Z interval is what we can do. Okay, so they do want you to show kind of the original setup. Remember, we always see those also on the multiple choice questions. So, show this stuff here. But then again, we're going to do a 2 prop Z interval. That's what we're going to do in the calculator. 2 prop Z interval. Yesterday we did a 1 because we had a 1 sample. Now we have a 2 sample. And then when we fill that in there, we get to put in our X1, N1, and then our X2, N2. And then we get to say what is our confidence, our C level. And that's typically what we have to type in. So the X1 and the X2s, that'll be if they gave us like, hey, 15 out of 30 girls, 14 out of 50 boys. Then the 14 and the 15s are our X1s and X2s. Okay, and then the other ones, the bottom numbers are our N1s and N2s. Now, if they don't, I think the example we're getting ready to do here, they just tell us the percentage of a sample. And so they actually don't give us what each of those things are. So we'll walk through on how to do that in a minute. Once we get done and we got our confidence interval, then we would go into the interpretation phase. And we would just start off the same way. We are blank percent confident that the interval from this to this captures the true difference in the proportion. Not the true proportion, but the true difference in the proportions of, and this and this is what we go through. Okay? So, anybody need any of that chicken scratch? Because I know I talk fast. Okay? All right. Let's do a problem together. All right. Are teens or adults more likely to go online daily? The Pew Internet and American Life Project asked a random sample of 800 teens. All right, so I'm going to let that be N1. N1 equals 800. And a separate random sample of 2,253 adults, so that's going to be my N2. 2253. All right. How often they use the internet? In these two surveys, 63% of teens, so my P1 hat was 0.63. And 68% of adults, so my P2 hat is 0.68. They say they go online every day. Construct and interpret a 90% confidence interval for P1 minus P2, okay, for the population parameter. So first off, as we go into this beginning stage, we will estimate the difference in proportions of teens and adults. So, that go online every day with 90% confidence. We will use a 2-sample Z interval for proportions, and then we're going to check conditions, if conditions are met. So let's check our conditions. All right, so with this in mind. Now, they did not tell us how many out of 800. So this one is why I always show the setting up of the multiplying. So I have to say, all right, 800 times 0.63. Are you greater than or equal to 10? So let me grab a calculator, do the math for it, have it next to me so we can have it handy. All right, so 800 times that's a negative sign, 0.63 gives me 504. So 504 is greater or equal to 10. Now I'd go over and do the is 800 times 0.37 greater than or equal to 10. So 800 times 0.37 is 296. Okay. So yes, the teens are normal. Beg to differ sometimes. Teens aren't usually normal. Then now I got to do the adults. 2253. Now, its percent was 68%. So 2253 times 0.68 would give me 1532.04. That is greater than or equal to 10. Don't worry about rounding. Okay, don't worry about rounding. It's okay to show that as a decimal. Okay. And then the next one, we would go 2253 times 0.32. Are you greater than or equal to 10? 2253 times 0.32 gives me 720.96. That's greater than or equal to 10. So yes, normal. Yes, normal. Normal condition is met. All right. Anybody need those numbers? I'm on like a half screen. Well, I guess I got a good calculator, thinner screen. Super narrow calculator. There we go. All right. Now, next one. Sorry. I did the random. I did normal. Sorry. I did that too in my notes. Normal. That one's random. I just straight getting into the math stuff. That's what I do. All right. Here they go. They said they had separate random samples. So we had a random sample of 800 teens and a separate random sample of 2253 adults. Okay. Independence. Independence. Guess I need to put more space in here. Let's see. 10 times 800 is equal to 8,000. 10 times 2253 is 22,530. All right, reasonable to assume. More than, are these US? Nope. So more than, so more than 8,000 teens and 22,530 adults who use the internet. Want to specify why? Not just that we have more than that, we know that, but it's reasonable to assume that there's more than that that use the internet. The context of our problem. Okay? So my conditions are met. Now I'm ready for find the stuff. Okay? So again, we'll show you two parts here. If I was doing, they asked us to do a 90% confidence interval. So the Z star for a 90% confidence interval. Our area, so I would do an inverse norm. Inverse norm. My area, 0.05. Mean is 0. Standard deviation is 1. So, again, if you're doing it by hand, getting the numbers, unless you memorize, if you memorize the number, just say table A. So, second vars inverse norm, because we want to show the setup. 0.05. Bump, 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 bump. My tail is to the left. And hit paste. So, boom. That is the, all right, so my Z star is 1.64. Again, you can stop there because that's what table A has. If you want to go out a little bit further and say 4.9, that's just going to make you more accurate is all it's going to do. Coach is going to switch away from that green since I'm on a split screen. All right, and then now my formula, we would go through and say, all right, they tell me that they classified the teens as P1 and the adults as P2, so I know now how to set up my subtraction. So I have to do the teens, 0.63, minus the adults, 0.68, those two P's, P-hats, plus or minus 1.64. Again, we can just use the 1.64, times the square root, now the big fraction, 0.63 times 0.37 over 800. Then I would go and say, all right, plus 0.68 over 0.32, times 0.32, sorry, times 2253. And then that's what I would do to start showing my work, okay? You do not have to simplify that all out. I'm going to go over here, grab my calculator, go into stat, over to test, go down to where I see a 2 sample, or it actually should be a 2 prop. Mr. Stevens, your fingers. 2 prop Z. 2 sample Z is for means, so we're not doing means. We're doing prop for proportions. And so I press enter. And so now I'm just going to type in. Now here's the challenge. We know for X1, we know what the X is. It's 504. My N1 was 800. Here's the challenge on the X sub 2. When we multiplied that out with 252 or 2,253 times 0.68, we got a decimal. So what you're going to have to do here is you're just going to have to do like 1532. If you put in the 0.04, it's going to give you an error code, is what the calculator is going to do. You're not allowed to put a decimal in for the values for the X1s and the X2s and that kind of stuff. All right? So now Again, it doesn't matter if we round down or we round up. It's still going to be close enough because it's keeping all the decimal places. And then now I put in my 2253. They said I wanted a 90% confidence interval. So I changed my C level. And then go down to calculate. And there we go. And I can skip straight to this decimal answer on my formula. I do not have to show the simplifying steps. Notice how they give me my P1 hat and my P2 hat in the picture in the calculator. Notice our P2 hat is like 0.67998. That rounds to 0.68. Okay, so we're close enough on that. So the difference would be just really minute between the intervals. It would be out in the 10 thousandths to 100 thousandths in the confidence interval, which means it's not really making a big deal. So now that we have that, now we're ready to write our statement. It says we are 90% confident that the interval from negative 0.0824 to negative 0.0176. Always do smallest to biggest. Okay, always do smallest to biggest as you do it. Capture the true difference in the proportion of teens and the proportion of adults. Notice they said true difference. That go online every day or use the internet. Okay? Now, what would we think? That has obviously got to be an older study. Right? Because this one's saying adults go online more than teens. Do you think that's still the case now? Or do you think that gap is narrowed? Instead of it being like 63 and 68%, one, I think both increases, but do you think there's that big of a difference of 5% between the two? I think it's probably a lot closer, especially because when we think about all the devices you all have in your hands and your fingertips, I don't know how old that study was, but if it was done I think about, my first cell phone was ancient, and it had like your long distance plan was anything outside the city, didn't have the internet, and so I didn't get text messaging on a phone until maybe 2007 on a phone, and that was the old flip phones where you had to press the number multiple times to change letters and stuff is what you had to do. And then eventually I got an iPhone 3 is what I eventually got when it came out. So then that kind of opened up the window to being able to get online a little bit on the phone. But that wasn't until maybe 2009. So, which is when you guys were like in elementary school, you got your same phone at the same time I did. We all got our same phones. We got things at the same time. You guys didn't get them at 2 years old?
No.
You see all the pictures now with these little kids and infants with their phones and stuff. So.
That actually freaks me out because I know that my phone gives me like brain rot.
Yeah, it does. It is. I mean, it truly is.